Good afternoon. My name is Irina Akhmadeeva, and I'm going to tell you about ontology-based information extraction for populating the intelligent scientific internet resources. Humanity has accumulated a huge amount of information related to various areas of knowledge. A great bulk of this information is available directly on the internet. However, the problem of supplying the scientific community with information of the interest has no satisfactory solution yet. This situation is partly attributed to the specifics of knowledge representation on the internet, which is weakly formalized, insufficiently systematized, and distributed among various internet sites, electronic libraries, and archives. Another reason is that modern information systems use a rather limited set of information representation methods. As a rule, that data and knowledge are represented in these systems as text or as a set of information resources. So, in our opinion, the most human-friendly form of information representation is a network of interrelated facts built on an ontology. This mode of information interpretation facilitates its perception and allows content-based search and convenient navigation through it. To solve this problem, we have suggested a conception of an intelligent scientific internet resource, which provides content-based access to systematized scientific knowledge and information resources related to a certain knowledge area and to their intelligent processing facilities. We call the ESIR an intelligent internet resource because not only information representation and systematization, but also all the functionalities of this resource are based on the formalisms of ontology and ontology inference tools. The ontology is the core of the ESIR knowledge system. This ontology contains a description of various aspects of the modeled knowledge area and a description of the structure and typology of information resources and methods of intelligent information processing associated with this area. So ESIR ontology consists of these three ontologies: ontology of knowledge area, an ontology of tasks and methods, and ontology of scientific internet resources. The structure of the content of the ESIR is based on the ontology. Information about the basic entities of a modeled knowledge area, relevant scientific information resources, and the web services implementing information processing methods is stored in the content of the ESIR. To keep the ESIR knowledge system up to date, it is necessary to develop methods for populating the ESIR with relevant information related to the ESIR knowledge area. The task of ontology-based information collection can be divided in two steps. The first step is information retrieval, and its aim is to find relevant resources in the internet. The second step, information extraction, focuses on extracting certain kinds of information from web documents. To implement this approach, we developed a subsystem automating the information collection about the basic entities of the ESIR knowledge area and relevant internet resources. The information collection subsystem consists of the following modules: the search module, an information extraction model, an information insertion model, a library of information extraction patterns, and a database for the storage of links to the relevant internet resources. The search model applies meta-search methods and retrieves links to relevant internet resources using the search queries generated on the basis of the ontology concepts and thesaurus. For every basic concept, a set of search queries are generated. Query templates for searching new individuals of an ontology class include names of classes, attributes, and relationships. Query templates designed to retrieve additional information about the existing individuals of an ontology class can also include the known values of attributes. The search model is invoked with a set periodicity. This model uses Google, Yandex, and Bing search system via the API. During searching, the efficiency of every search template is evaluated on the basis of the number of retrieved relevant links. The more efficient a template, the more frequently it is used. Since the search model makes use of general-purpose search engines, it is necessary to filter web documents non-relevant to the knowledge area. Relevance of a link is evaluated using characteristics vectors built both for the search query and the web page downloaded by its link. Names of ontology concepts close to the concepts contained in a query are included in the query vector. The relevance of a web page with respect to a query is calculated as the value of cosine similarity measure between these vectors. At the second stage, we extract from relevant web documents information about entities of the ECR knowledge area presented by the individuals of ontology classes. Information about projects, conferences, persons, publications, and organizations is extracted at this stage. The web documents can be presented in various formats. However, since HTML is the main format for information representation on the internet, the proposed methods were designed for HTML pages. As a rule, information extraction methods dealing with HTML pages extract information using the text of these pages. The templates used in these methods are usually defined by a set of paths on a page, which allows extracting similar data from one site. The disadvantage of this approach is that these templates are strongly dependent on the structure of the page, which is specific for a site. A slight change in the page structure can disable the template so that it cannot extract information from this page. Moreover, in order to extract information from a new site, it is necessary to build automatically or manually a new site-specific template. The main idea of our approach is to eliminate the use of text in the templates. Instead, we define common elements for all HTML pages and extract information on their basis. These elements are described in the ontology of the web document structure. For example, these elements is main content, web page footer, sidebars, header, or site menu, and others. This ontology is used for constructing patterns for information extraction and for analyzing web documents. For this purpose, the methods based on the analysis of DOM3 of the page are developed. The document object model is an API that treats an HTML document as a tree structure wherein each node is an object representing a part of the document. Note that such technique as Ajax complicates the analysis of web document structure because its DOM3 changes during script execution. Ajax is a web application development technique for dynamically interchanging content, and it sends requests to the server for data in order to do so. Usually, libraries which allows working with DOM3, constructing it on the basis of HTML source, but ignoring scripts on the page. One of the possible solutions is to render a HTML source of a web page in a browser. One of the advantages of this approach is that it solves the problem with dynamic content. Besides it, it is possible to obtain visual characteristics of DOM nodes, which can be helpful in page analysis. A disadvantage of this approach is that it takes a lot of time. For this purpose, we use the Selenium WebDriver tool, which allows us to interact with the browser and analyze a DOM3 in its final form. We use a Phantom.js headless browser, and for test we use the Chrome browser if we want to see results right on the page. To analyze the DOM3 of pages, two methods were combined: the methods using heuristics and logistic regression. For each type of elements of the ontology of web documents structure, heuristic methods was developed, which determines whether some subtree of DOM has this type. For example, site menu should contain a large number of links, and these links should point to the same domain. Main content of the page should contain a lot of text and a small number of links. Moreover, class and ID attributes of node can be helpful in detecting main content of the page, because web designers often give them meaningful names. Unfortunately, heuristic-based methods doesn't show good recall in extracting main content. To extract main content of the page, another method based on the machine learning was developed. we use logistic regression classifier to train the classifier for each node of DOM tree. A number of features were calculated, such as the length of the text content, the number of siblings nodes, the number of images of the parent node, the number of links, the depth of a node in the DOM tree, and others. To compare these two algorithms for main content extraction, the performance of them was calculated. Recall precision and F1 measure are shown in the table. The logistic regression classifier shows better recall with almost the same precision. So for main content extraction, we use logistic regression classifier. For others, web page element detection, we use heuristics. Information extraction pattern is an XML document that contains markers defining in it the position of individuals, relationships, and attributes. Each pattern is described by a class block and contains attribute blocks, relation blocks, and arguments of relation blocks. Each marker from pattern includes a term of the thesaurus, a page element that should contain this term, and a page element that should contain information of interest to this marker. So in the process of information extraction, after analyzing an HTML page and selecting its basic elements, information is extracted in accordance with an information extraction pattern. Thus, during the pattern recursive processing, corresponding elements of an HTML page are extracted. The experiment showed that the performance of the whole subsystem of information extraction largely depends on the performance of the page analysis algorithm. To test our system, we collected information about persons, organizations, conferences, and projects from Russian and English websites. On the slide, the example of extraction information from the dialogue conference. Another example is shown on the slide. It is process of extraction of information about project General Internet Corpus of Russian. Annotation is extracted as a block following heading, including term about. Extraction of publication about project requires downloading a new page, obtaining by its link in the site menu containing term publications. Result of information extraction process is in the XML format you can see on the slide. This work presents an approach to collecting information about scientific activities from the internet in order to populate the intelligent scientific internet resource. The proposed approach combines meta-search and ontology-based information extraction methods. Experiments have showed that the proposed approach is promising, but further efforts to develop this approach should focus on improving the HTML page analysis methods and on developing methods for extracting information from the documents of various formats other than HTML. So that's all. Thank you for attention. Questions, please.
Thanks, Irina. Questions, please.
Is there any solution you can compare your solution with about, and I'm speaking about the page analysis, the one that you use, where you use heuristic and logistic regression approach?
Can you repeat the question? I didn't hear.
You have two algorithms that you use for the page analysis.
Yes.
And could you tell me if there is any solution in the related world or anywhere else that you could use for comparing the accuracy of your results with the results in those applications that are?
There are many approaches to detect the main content on the page. Some of them use machine learning, some of them use heuristics, but we didn't compare our algorithms with them. But it's good questions.
More questions?
I just didn't understand what are you classifying? Classifying what within this?
We classify leaf nodes of DOM tree as into two classes as belonging to main content and not belonging.
Relevant or not relevant? What is belongs?
Not belongs to the main content of the page, or it belongs to the menu of a page, or its footer, or its header of the page.
We have time for one more question. No questions? Then, thank you, Irina. Oh, Peter?
Okay, thanks a lot. So next session is over, half an hour break, and at 4, Axel Polaris will give us a keynote, so be ready.